So let's talk about radical functions. But, instead of cracking open a dusty old textbook, we're going to start somewhere completely different, a real-world high-stakes scenario. Believe it or not, this exact formula is what scientists at the Pacific Tsunami Warning Center are looking at. It's pretty amazing, right? The speed of a tsunami, it all comes down to the square root of gravity times the ocean's depth. So they measure the water levels, plug it into this radical function, and boom, they can figure out how fast that wave is moving. And that calculation, that's what predicts its arrival time, giving people that absolutely crucial window to get to safety. So you have to wonder, what is it about this one little symbol, the radical, that holds so much power? What makes it capable of saving lives? Well, to figure that out, we've got to decode the amazing mathematical tool hiding behind it. Okay, so let's do just that. Let's pull back the curtain and really get into what this symbol is all about. What is it, really? And where does all that power come from? So at its core, a radical function is just any function where you've got a variable tucked away under that root symbol. And the term for what's inside, that's the radicand. But here's the key thing to remember. A square root is really just the opposite of squaring a number. It's inverse. They're like a perfect pair that undo each other. You square something, then take the square root, and you're right back where you started. And check this out. You can see that inverse relationship perfectly in this table. Look over on the left for y equals x squared. You put in a 2, you get out a 4. Simple enough. Now jump over to the right, to the square root function. You put in a 4, and what do you get? You get a 2. See that? The inputs and outputs literally just swapped places. That is the classic calling card of an inverse function. And that inverse relationship, that is exactly why the graph of a square root function has that specific shape. It's not just some random curve. It's literally half of a parabola that's been knocked over on its side. It's a perfect reflection across that diagonal line, y equals x. Okay, so now that we know what it is, we've got to talk about the rules. And there is one single rule, the one rule you absolutely, positively cannot break when you're dealing with square roots. And here it is, the big one. You cannot put a negative number inside a square root, ever. And why is that? Well, just think about it for a second. Can you think of any real number that when you multiply it by itself gives you a negative result? A positive times a positive is positive. A negative times a negative is also positive. See? It just doesn't work. And this one fundamental rule, it dictates everything else about how these functions behave. So this rule directly leads us to something called the domain. And don't let the fancy word fool you. The domain is just the set of all the possible x values you're allowed to plug into the function. It's like the list of approved guests. For the most basic function, the square root of x, the domain is super simple. X just has to be 0 or anything bigger than 0. And the great thing is, finding the domain for any radical function is always the same simple 3-step recipe. Step 1, you take whatever's inside the radical. Step 2, you set it to be greater than or equal to 0. And step 3, you just solve for x. That's it. That tells you your entire safe zone of inputs. All right, so we've got the rules down. Now let's see how those rules come together to build the actual visual blueprint of the function on a graph. So take a look at this shape. Get familiar with it, because every single square root graph you will ever encounter is just a version of this one. We call it the parent function. F of x equals the square root of x. It always starts right there at the origin, at 0, 0, and then gracefully curves up and to the right. Seriously, once you know this one shape by heart, you can graph any of them. So what happens when we start messing with it? Well, if you add or subtract a number times inside that radical, right next to the x, you're not actually changing the curve itself. All you're doing is sliding the whole thing sideways, either left or right. And what do you think happens if you add or subtract a number outside the radical? You probably guessed it. The whole curve just moves vertically, up or down. It's really that predictable. And once you get the hang of these simple shifts, you've unlocked the secret to graphing any radical function you come across super quickly. Okay, so we've learned the shape, we've learned the rules, but so what? Why does mastering all this actually matter? Well, this is where we get to the real payoff. It turns out it's not just about calculating tsunami speeds. Radical functions are like this hidden toolkit that professionals are using all the time in all sorts of fields you might not expect. We're talking business, finance, medicine, engineering, the list goes on. Take medicine, for example. Doctors actually use a formula with a square root in it to calculate a patient's body surface area. And why do they need that? Well, it helps them figure out the exact right dosage for certain medications. It's all about making sure the treatment is not only effective, but totally safe. Or how about finance? Planners use a formula that's built on radicals to figure out the real annual inflation rate on something big like a house. They can compare its price today to its price years ago and get the true story. It's a way to see right past the sticker price and understand the actual financial reality underneath. Okay, last but not least, let's talk about actually solving equations that have radicals in them, because there is a fascinating and kind of tricky little twist here that you absolutely need to know about. So there's a pretty clear four-step process for this. First, you get the radical all by itself. Then you square both sides to make that radical sign disappear. Then you solve what's left. But that fourth step, that last one, checking your answer, that is without a doubt the most critical step of them all. And here's why. Because sometimes when you square both sides of an equation, you accidentally create an answer that looks perfect, but it's actually wrong. It's like a mathematical ghost. They call it an extraneous solution. And it happens because squaring things can, well, it hides information. Think about it. If you square 2, you get 4. If you square -2, you also get 4. So the process of squaring can spit out a solution that works for your new equation, but would have required a negative inside the original square root. And what did we say was the number one rule? No negatives allowed. Which really leaves us with this one fascinating question, doesn't it? How can an answer that you found using perfectly correct math steps actually be wrong? It's just a powerful reminder that when you're working with the power of radicals, you always have to circle back and check if your answer actually makes sense in the real world of the original problem. Because sometimes the math itself can take you on a journey and create answers that were never really there to begin with.